Hi, I'm Dave Miller, and I'd like to chat with you about your backpropagation neural net. This is a companion video, a follow-on video to one that I released a while ago about a C++ implementation of a neural net. And in that hour-long video, we talked about the implementation, the coding, but we didn't get a chance to talk about how to use your neural net to solve other things. And so this time in this video, I'd like to chat with you about how a neural net actually works at the nitty-gritty level, and then how to set up new training data to have it solve other new problems. We'll talk about how to set up the input ranges and the output ranges of your training data, and some strategies on how to train your neural net to find a solution to various kinds of problems. And then I would like to leave you with a visualization, sort of a graphic, geometric visualization of how a neural net actually learns to do anything at all. And I'm hoping that after the end of this video that you'll feel a little bit more comfortable intuitively about how that a neural net works and how to train it. So just as a quick review, a neural net takes a set of values on its inputs and it gives you some answer on its outputs. That mapping now that goes on from the input to the output is something that the neural net has to learn to do by from repeated exposure to your training data. For example, here's a little trivial neural net. It's got 3 layers. This is the input layer. It has 3 neurons, but you'll make yours with however many neurons you need to accept all of your input data. And this is the output layer. It has however many neurons you need to output all of the components of the answer that you're trying to train it to give you. For example, suppose this is a controller. Say this is a controller for an exhaust fan that's on an experiment that you're running in your secret underground biolab. The inputs come from 3 sensors, and you need to monitor the ambient air temperature, the humidity, and the barometric pressure so that you can output a binary signal on the neural net that turns the exhaust fan on or off. And it's really critical that the exhaust fan get turned on and off at exactly the right situations of atmospheric conditions. Otherwise, you'll ruin your biological experiment. And so what we'll do is we'll train the neural net to output a binary signal, and if the output is above 0, we'll accept that as a fan on signal, and if the output is below 0, we'll accept that as a fan off signal. That's the kind of thing now that we do with a neural net. The neural net at first won't know when to turn that fan on or off until you train it. So you'll prepare a file containing hundreds, maybe thousands of just examples of various combinations of input values and what the output value should be for each of those cases. And after enough training, the neural net will finally figure out what that mapping is from input to output. In your training data here, I call each row of this table a training sample. Each training sample has a set of inputs and then what you have determined the output should be. And each time that we present one of these samples to the neural net for training, I'll call that one training pass. We need as many training samples as we can collect, and we need to present them to the neural net at least once per sample, sometimes repeatedly, and then we'll just keep training the neural net until it finally gets what that mapping is from input to output. We'll talk more about training strategies here in a moment. But we need to ask a question here at this point. Is this application, I mean this specific application of inputting temperature, pressure, and humidity in order to control a fan, is this a good application for a neural net? And, well, the answer is, it depends. It's not a very good use of a neural net if you already know what the formula is. Suppose you already knew that the fan should come on when, some formula like temperature times 0.9 minus twice the humidity divided by the pressure over 2.4. And if that's greater than 2.9, then the fan is supposed to come on. Some weird formula like that. If you could figure out that formula, then you don't need a neural net. Just make a circuit or write a program that does that formula. The only time you need a neural net is if you know example cases of what should happen, but you're not quite sure what that formula is or how to even derive that formula. And then you just give the examples to your neural net and let it figure it out. And sometimes it's just like magic. Sometimes a neural net will look at your examples, and after a while it's almost as if it understands what it is that you're thinking and how that you're judging those inputs, and it starts solving the problem for you. But other times you put together a neural net to solve a problem and it turns out to be just as dumb as a rock. So how does a neural net work? How does this collection of neurons and connections learn how to solve anything at all? And what are its limitations? And how would you train it to solve different kinds of things? So to answer these questions and to understand more intuitively how the neural net works, It's probably helpful if we spend, first of all, just a couple of minutes analyzing in very close, fine detail how a very trivial neural net works, and then we can expand that and generalize that to more complex situations. The absolute most trivial neural net that we could construct would be one that has one input neuron and one output neuron and one connection between the two, and it has no bias. Now, we'll talk more about biases later, but for right now, there's no biases. What you see here is all that there is. One input, one output, one connection. The connection is weighted, so it has one weight. We'll call that W1, because one weight. This neural net then has an input layer with one neuron, an output layer with one neuron, and no hidden layers in the middle. The input is just a latch. Think of the input as just a floating point number, and this neuron just latches onto it and passes that number through to its output. This green connector is a weighted pipe. It's just a floating point number too, which is just a factor that gets multiplied by the input number through this, that goes through this neuron on the way to this one. Now this output neuron adds up all of its weighted inputs, which is just a single one here, and that means that this neuron sees this input number multiplied by this weight factor, and then it passes the result through this activation function to produce the final output number. The activation function is just some sort of a curve. It might be like this one. It takes whatever the neuron sums up on its inputs and then converts it to some number on the output between the limits of this function, which ranges between -1 and +1. The only thing we can adjust on this neuron is the weight on the connection between the input and the output. In any neural net, all the connections between the neurons are all weighted, and then during training, the weights are incrementally adjusted until eventually they turn the whole neural net into the function that you want. The weights are what make a neural net solve anything. In any neural net, a solution is just a collection of all the specific weights that overall make the neural net perform some specific function. After a neural net then gets successfully trained, then you can just freeze all the weights, and then the net should hopefully perform just as accurately when it is presented with new input data that it's never seen before. Now on this most simple neural net here, let's say you set the weight to 0. What does that mean? That means that no matter what the input value is, it gets multiplied by 0. This neuron sees 0 and always outputs 0. That would turn this neural net into an overall function like f of x equals 0, where x means your input data. So this overall neural net then would be operating the function f of x equals a constant 0. And that's certainly a solution to some problem, but probably not a very interesting problem. What else can we train this most trivial neural net to do? Can we train it to say, let's say let's say the identity function, f of x equals x, where we just pass the input to the output. Can we train it to do something that simple? You can almost intuitively see that a weight of 1.0 might be close to a solution. Let's try that. Let's set W1 to 1 and let's see what happens. Then any input that we input here that's close to 0, plus or minus a little bit, will get passed right through this neuron, through the output with very little change because it passes through the activation function in this area where it's almost linear. For example, a 0.5 on the input times 1, a 0.5 then passes through this transfer function here at about 0.46. That's pretty close. So inputs in the range of about minus 0.5 to plus 0.5 will pass through this function almost unchanged. And then the error gets worse as the input values are farther, above or below that range. So for this particular most trivial neural net, the accuracy might be acceptable for some particular problems if you restrict the inputs to a certain range. And then the answer to our question is a qualified yes. This neural net can function as f of x equals x if we constrain the input range to a certain small range. And then it's just an approximate function. So what else could we do with a neural net? Now, that last example was an example of an analog kind of a problem, an analog input and an analog output. But what about a binary kind of a problem, a Boolean problem, where we have Boolean inputs and true-false outputs? Could we train this most trivial neural net to become, let's say, like a Boolean inverter, where a true in results in a false out and a false in results in a true out? Well, first we need to decide on what two values that we can use to represent the two Boolean values of true-false. And of course, there's nothing special about using zeros and ones as binary digits. Any two distinct values are just as valid logically. For the input layer, it doesn't really matter. Any two distinct values on the input will work because a neural net can adjust the weights during its training to scale those values to whatever it thinks it needs. Inputs of +1 and -1 are reasonable choices for true-false inputs, or 0 and 1 will work too. The output values are trickier. The easiest thing on the output is to train the neural net to output the extreme values of either +1 or -1 for your two Boolean states, or actually whatever the limits are of the activation function that you're using. If you were to replace the activation function with one that ranges from 0 to 1, then you should then train the net to output zeros and ones. But here, let's just stick with the example that we started with of using a function that ranges from -1 to +1. And so the easiest thing and the most successful thing to do is to train the neural net to output those two values for Boolean values. Now, if you did try to train this particular neural net to output, say, 0 and 1 as its Boolean values, it'll get the 1 right, but in order to output 0, it has to learn how to adjust its output weights to just a very particular exact value so that those answers get passed through the activation function right at the 0 point. But if you train it to output the extreme values of 1 and -1, then it's allowed to come up with any kind of weights that swing the output way to the side or way to that side to represent the binary result. So it has more latitude to come up with answers. So you can kind of see intuitively that, yes, this most trivial neural net could work as a binary inverter if the weight were some negative number. So take, for example, let's just say for fun that this weight were, say, -1. Now what happens? An input of +1 then gets flipped by the weight to -1, which passes through the transfer function and results in an output of -0.76. And an input of -1 gets output as +0.76. And that's perfectly good enough to be a binary inverter if we're okay with the two output states being plus and minus 0.76. That way, you train your net to output plus and minus 1, but then after it's trained, you allow it to be a little sloppy, and then you interpret anything above or below 0 as true or false. But the longer you train it, is the closer that the outputs will learn to be +1 and -1. As you train this neural net, this weight here will start growing to a greater and greater negative number, and eventually it'll grow larger. Let's say once it reaches -10, then look what happens. Then an input of +1 gets multiplied by 10 and gets sent through the transfer function and results in an output of 0.9999996. And so that's pretty close to 1. So it's just over a long period of training that the outputs would become closer to your targets of 1 and -1. And then if you're willing to interpret the outputs after training, if you're willing to interpret the output as anything above or below 0 as being true or false, then you can also look at the absolute value as maybe a confidence measure. And this all kind of depends on your particular problem and your input data and how well the net was trained. But it's possible that perhaps maybe that you could regard it something like a 0.9 output as true and a very confident true, but an output, say, of -0.2 then might indicate that the neural net thought it was false, but kind of with not a lot of confidence in that particular answer. So you might get you might get a little extra benefit from your neural net, not only an answer, but also a confidence measure. What else can we do with this most trivial neural net? How much can we get out of this most trivial neural net? So let's take a practical example here. Suppose that you're a do-it-yourselfer and you're wanting to build your own temperature monitor that monitors the temperature of the coolant water in your backyard nuclear reactor. You want to train your neural net to sound an alarm if the temperature ever exceeds 95 degrees centigrade. Below 95, there's no alarm. Above 95, we sound an alarm. This problem here now is we have an analog input and a binary result. What we want to do is train our net overall to function as f of x equals 1 if the input is over 95 and -1 if the input is under 95. Can we train this most trivial neural net to do this formula? You can think about that a bit if you want to, but I'll tell you right now, it'll be trivially easy if we make a small modification to our neural net structure here. If we just add a bias into this output neuron like this. Now we've got two weights, W1 and W2, W1 for the input and W2 for the bias. The bias input is just a constant value like 1.0, but it's weighted like the other inputs to this neuron. From this neuron's perspective here, it's just another weighted input, just as if it were another neuron from the preceding layer. In fact, one way to visualize this mentally is to picture it as another neuron in the previous layer. So I'll just draw it like this. We don't have to include that neuron in the training input data because it's always set to a constant 1.0. It's an abstract, under the covers invisible neuron just for handling the bias in a convenient way. And you can generalize this particular concept to larger neural nets. Here's what those biases would look like in a larger neural net. Each layer, except for the output, would just have one more of these fake neurons that supplies a constant value through a weight into all the neurons of the next layer. There's lots of ways that you could program your backpropagation neural net to handle these biases, and this is just one way to visualize the way that they're connected. And it's also the way that I suggested implementing it in code in the other video, because then the forward propagation loops and the backward propagation loops can deal with updating those connection weights on the biases just along with all the other weights, just like any other neuron weights. It makes the code loops simple that way if we don't have to write some special code to handle the bias weight adjustments. Back to our trivial neural net. Now you can kind of see what the weights might need to be. Let's say that W2 were minus 95. Now that means that always this presents a minus 95 that gets summed up with the other input at this point. Then that means that the output will be below 0 if the input is under 95, and the output will be above 0 if the input is above 95. Suppose W1 were just 1. Then what happens if the input temperature is just a little below 95, like 94? Well, the 94 gets summed up with the minus 95 here, resulting in a minus 1, and so the output then is over here on this part of the activation function. Or let's say the input were just a little above 95, like 96. So then that 96 gets summed up with minus 95, and then it's a positive 1 that gets sent through the transfer function onto the output. So any positive W1 weight will solve this problem if we interpret the output as anything above 0 means alarm on and anything under 0 as alarm off. Let's do another practical example here. Let's say that you're working on your cruise missile and you're wanting to design a new temperature monitor. You know that temperature monitor that monitors the temperature at the pulse jet exhaust? So you want this temperature monitor now to assert an emergency signal on its output if the pulse jet exhaust temperature ever exceeds 340 degrees centigrade or ever is under 320 degrees centigrade. Either way is a bad situation. Between 320 and 340, no alarm output. Any other value, though, and we assert an alarm output. So here's a graph of the function that we're trying to train the neural net to achieve overall. Can we train this neural net to perform this function? Well, you can think about that a little bit if you want to, but I'll tell you this much. It's going to be a lot easier if we add a hidden layer in here and add a couple more neurons in the middle, in the hidden layer. Now we've got a couple pathways that we can take in here. We can see that if this neuron here had a bias of minus 340 and a large weight on its other input, then its output will be driven high when its input is above 340. And on this other side here, if this inner neuron had a bias input weight of minus 320 and some large negative weight on its other input, then it will drive its output high when its input is under 320. Then the output neuron just serves like an OR operator that drives its output if either of these alarm conditions are activated by either of these inner neurons. So this means that an input above 340 goes through this pathway and results in an alarm asserted here, and an input of under 320 will go through this pathway and assert an alarm output here. So we've achieved this function, but we needed to add in some extra smarts to the neural net to do that. So the takeaway message there, the moral of that story is, give your neural net enough smarts to do the job adequately. So let's take another practical example here. Let's say that you have a chocolate chip cookie business and you just can't make enough cookies to meet demand. And you've had to automate in order to make enough cookies. And in your automation factory here, there's a place where there's a conveyor belt that conveys baked cookies from the oven over to where they get bagged and boxed for shipment. And there's an inspection camera that takes pictures of your cookies as they pass by on the conveyor belt under the camera. And here's an example. Here are 8 different pictures of cookies. And I didn't go out and take actual photographs here for this, so just pretend these are real pictures, okay? Work with me on this. So pretend these are 8 pictures of cookies. And what we want to do is we want to train the neural net to accept this one, this one, this one, this one, this one. And it will reject this one and this one because they're not nice and round. They're irregularly shaped. And this one here, this one could be a judgment call. This one's kind of small, and so you could train your net to reject the small ones like this. That's just a judgment call on your point. Just be consistent in your training. If you train it to reject this one that's small, then be sure to train it to reject all other similarly small cookies as well. Now our question is, how do we present the information from the digital camera to the input neurons, and how do we train this neural net to do this kind of pattern recognition? In principle, we could just take each red, green, and blue pixel value from the camera and just route each one to an input neuron. But that could require a lot of input neurons. Suppose your input image is 512 pixels by 512. For RGB components, that's 3 times 512 by 512. That's 700,000 input neurons you would need. Now, you could do that, and in some cases that might be a perfectly reasonable thing to do with your neural net, but you don't need to in this case with these cookies. The net doesn't need that much information to do this kind of pattern recognition. And in fact, if you give your neural net too much redundant information, the neural net is going to have to sort through all that excess information and discard everything it doesn't need in order to extract the salient information from your inputs. So you want to refine your input data to just the information that the neural net needs without a lot of redundancy. So what does the neural net need to recognize cookie shapes? Well, first of all, it probably doesn't need the color, because with a lot of pattern recognition, shape recognition problems like this, visual recognition problems, it depends more on contrast than color. There's a lot of redundancy then in the red, green, and blue channels for this particular problem, and there's no need to inundate our net with all that redundancy. So we could just take one of those color channels or a monochrome signal and then input those pixels into the neural net. Also, it doesn't need this much resolution. You'd be surprised at, in some cases, how much information a neural net can extract out from very low resolution imagery. It's really amazing sometimes. I'm going to go to extremes here because I want to be able to show a diagram of a neural net on the screen here, and we have limited screen space. So just for illustration, I'm going to illustrate reducing the resolution here of our pixels down to an extremely low resolution, like 2 pixels by 3 pixels per picture. I mean, we're talking about a total of 6 pixels now per cookie picture. And you know what? This might almost be enough resolution for this neural net to learn this kind of pattern recognition. You might need a few more pixels than just 6 pixels per cookie, but it might almost just be enough. So here's how we connect them. We take each cookie picture, which we've now converted to monochrome, and we just run this pixel value into the one input neuron, this one into another neuron, and we just connect them all up like this. Now our next question is, how many training samples do we need to train the neural net to do this kind of pattern recognition? And the answer to that, as you probably can intuit, is it really depends on the specific situation. Each problem is unique, and it depends on how much information the neural net has to extract from this data, how much difference there is between different cookie shapes, how fine a difference there is between a good cookie and a bad cookie, and how much noisy data there is in the input stream, how the characteristics of the camera, its contrast, and how consistent you labeled the training outputs during your training data. In the ideal situation, you might just need 100 training samples of cookies. But in a tougher situation, you might need many thousands or sometimes even tens of thousands of training samples if you're trying to get the neural net to extract out some really tricky data from the input. So the moral of this story is collect as many input samples as you comfortably can, hundreds at least, and then trial and error. If that doesn't seem to be enough to get your neural net to converge upon a solution, then perhaps it needs more samples. Here's what happens when you train your neural net. In each training pass, you'll present your training sample inputs to the neural net and let it produce some answer. Then the answer will be some difference from what you've said the answer is supposed to be, so you take the error difference, and then that's what the backpropagation is all about. The backpropagation goes backwards through all of the connections, updates all of the weights by a tiny amount in the direction they need to go to make a better output for that training sample. And then it's only through many repeated training passes that the weights will eventually get corrected to something that works with a small error on all the input cases. So the moral here is mix up your input training data. Collect as many samples as you can, label the outputs what they're supposed to be, and then mix them all up in some mixed up random order and present those to your neural net, not just once, but maybe even multiple times, and keep randomizing the order each time. And you might need to present all of your training samples many, many times to your neural net, but eventually then, if you're successful, those weights will all converge to a set of weights that work with a low error on all of the training samples. Now, one little trick that you can do is you can collect all of your training samples and then set aside a certain percentage of them, like half of them or 20% of them or 10% of them, as test cases for after you've stopped the training. Then take the other samples, use those for training until you finally get what seems to be a good solution from your neural net. And then freeze all of the weights and use those training samples that you've set aside in order to see whether or not your neural net can continue working accurately on data that it's not seen before. Because sometimes the neural net can come up with a solution that works really well just specifically on your training input data because of some statistical little accident of the training data that you didn't even see. The neural net can find that and exploit that. And so just to test to see that it has come up with a generalized solution to what you think that it's solving, then you can use those, you can set aside some training cases to do that kind of a test later. So how does it all work? Now, we've seen how that a very trivial neural net works at a very low mechanical level, but how does a larger neural net work? When you put together more neurons and connections, how does it solve any kind of a more substantial problem? And I hope to give you a way to visualize that here a little bit. Let's start off by visualizing what happens with the weights on our most trivial neural net that's got two weights on it like this, a W1 and a W2. This plane here represents every possible value of W1 and W2. The center point here is where W1 and W2 are both 0. W1 gets bigger this way and more negative that way, and W2 is orthogonal. These are floating point numbers, W1 and W2, so they extend a long way out there off the screen in all four directions. Here, for example, is where W1 is some small negative value and W2 is some other negative value. This little red marker then shows that combination of W1 and W2. Now we can call this kind of a diagram the solution space to our neural net. Our neural net has two weights that can be adjusted, and so this is the entire space of all the possible states that our neural net can be trained to be. For example, if this is a neural net that has been trained successfully, and we have found the place where there's a good solution with W1 and W2, we could show where that point is with a vertical bar right here at that point, where high means a good solution. The vertical direction means accuracy or success. And sometimes, as we've seen in the previous examples, the weight doesn't need to be just one particular pinpoint value to be successful. Sometimes a weight just needs to be larger than some number or smaller than some number. Remember the previous example that we did of your pulse jet exhaust temperature monitor. It had two weights, and the solution there meant that the landscape would look something like this, where W2 would be best when it's minus 95, but W1 could be anything above 0. So you end up with a solution contour here that's sort of a ridge like this that extends in a big long hill that goes way off in that direction. Remember now that we're just looking at two dimensions here for two weights for a very tiny neural net, but you can generalize this. For a more complicated neural net, you'll have a lot of dimensions, a dimension for every weight, and the solution contour will be a very highly dimensioned contour, and it could be very much more complex than this. There could be lots of locations of relative goodness, and it could be just a really complicated hyperdimensional contour. But we're just showing here two dimensions, and I'll leave it up to your imagination to try to imagine a higher dimensional space. And here, as we go on for discussing, I'd like to show you a solution landscape. This is a possibility. You might have a couple of dimensions in the solution landscape where there are a couple of points where there are good solutions. I'll just show two hills. This represents two places where there are pretty good solutions. One is better than the other. You can probably realize at this point that we could invert our thinking and think of this landscape as an error rate where lower values are better. So then the good solutions would be valleys and pits like this. And in many times when we're discussing neural nets, we'll talk in terms of error rate. And so then you'll need to think in your mind a landscape like this. Whenever you read about or talk about gradient descent in reference to neural net, the gradient descent that they're talking about is a descent into one of these valleys of low error. And whenever you read about or you hear talk about a local error minimum, that refers to a little valley of somewhat low error rate, like this little depression here. And so sometimes you can think in your mind a visualization this way. And if you like to think of it this way, then turn your laptop upside down, because I'm going to reverse it and show the landscape this way now, where the z-axis means up, means success. Because, I don't know, it just looks to me more uplifting, more encouraging if it has to go uphill to reach the better solutions instead of falling into some dark pit. So these graphics here now use a z-axis that means success, or accuracy is upwards, which is the inverse of error. So what happens during training? Well, during training, your net has to start out with some weights of some kind. They're floating point numbers, and they have to have some starting values. So they could start out anywhere here on the whole map. Let's say they start here. And then when you present a training sample to the neural net, the backpropagation algorithm will adjust the weights a tiny bit in some direction, say this direction here, like that. So what does this mean? This means that if you were to present the exact same training sample to the neural net again immediately with these newly adjusted weights, it would produce a slightly better answer, one a little closer to the desired output for this training sample. But take note that the adjustment that was made was only based on the current training sample. The amount that the weights get adjusted might or might not be better for all the other training samples, and that's why you need to give it a lot of training samples. The very next training sample you give it might reverse the correction, correct it in a different direction like this. And then the next one might correct it in a different direction like this. It's only by accumulating hundreds or thousands or millions of corrections that the weights finally settle upon one of these solutions represented by the hills. During training, the weights are going to jump around like, I don't know, like grasshoppers on a hot hyperspatial sidewalk, or like a drunken programmer. And so it's only by accumulating a lot of these errors that eventually they start heading over toward one of these solution hills. And now with this visualization, maybe you can also see how the tunable parameters work. There's a learning rate parameter in most neural nets, and in the other video I called this particular parameter the eta parameter. And that determines how much correction to apply after each training sample. If you have a high eta value, that means that the correction in each training sample will be larger, and the weights then will tend to gallop across the landscape toward a solution faster. But the trade-off is once it reaches one of the good solution places in the landscape here, it could just gallop right over the hill and right past it and not even find it. Or the weights might jump all around the hill, around the good solution, but never really settle upon the middle of the good solution. So if you had a lower eta rate, then it takes smaller baby steps as it's traveling across the landscape. It will take a lot longer to get to one of these good solution hills, but with a low eta rate then, it's more likely to do a more accurate job climbing up the slope and finding where the very center of that slope is. So maybe this suggests now a strategy you can take with the learning parameter. One strategy is to write your neural net program so that it starts off with a high eta rate at first. That lets the weights gallop across the landscape, and then as soon as you detect that the error rate is starting to jump wildly up and down, that means that it's in the middle of some hills that it's trying to climb, and it can't quite climb it really well. So at that point, lower the eta rate, and that way it gives it a chance to take small baby steps, and it can climb up those hills and reach the middle of the top of the hill a lot more accurately. The other tunable parameter is the momentum rate, and in the other video I called that the alpha parameter. And what that does, that just amplifies a correction if if the correction in the weights is in the same direction as the last correction from the last training sample. So if you had two training samples in a row that caused the weight to be adjusted a little bit in the same direction, then a high alpha momentum parameter means that it will get amplified and that correction will be applied at a greater amount. And that could help out at the beginning of training if to allow the weights to gallop across the landscape. And just like the eta parameter, that's one that probably you want to lower and keep low once it starts climbing up a solution. Otherwise, it'll tend to jump around too much and not really settle upon a good solution. And you can probably imagine the worst case situation would be that your data just accidentally results in a solution contour where there are many small local solutions, but then only one good global solution mixed in somewhere in the middle of all those. And you can see it would be really hard to come up with an eta and alpha parameters that will let the weights wander around, avoiding all of those local solutions and arriving at the one good global solution. So if you have data like this, you could try maybe starting your training session over several times with different initial starting weights. That way the weights start at a different part of the landscape, and perhaps then during one of those attempts, it will accidentally find that one good solution. Another strategy, which might even be more effective, is to take a look again at the input data that you're giving to your neural net. Maybe there's some additional information that you can provide on the inputs that will give the net a better chance then to come up with a solution. But anyway, that's all the time that we have today for this video. I hope that this discussion has helped you come up with a better intuitive feel for how the neural nets work. And I hope that you're able to use this information in your programming projects. And I wish you the best of luck in all of your programming projects and a lot of fun. Thanks for watching. See you next time. Bye.